Open any high school biology textbook, and you'll likely find the same story about the origin of life. A lightning bolt strikes a warm primordial pond, sparking a chemical reaction that immediately produces a perfectly formed swimming cell. But the early Earth lacked an ozone layer. During the Hadean Eon, intense UV radiation and extreme temperatures would have degraded unprotected organic compounds as quickly as they formed. This ocean model introduces the dilution problem. Individual molecules are separated by billions of gallons of water, making meaningful collisions statistically improbable. For chemical networks to initiate, raw materials must constantly interact. But even as shallow pools evaporate, vital components remain too dispersed. There is also the problem of hydrolysis. Liquid water facilitates a process that actively breaks the chemical bonds in proteins and RNA, the very building blocks early life needs to assemble. Raw chemicals floating in a giant ocean cannot spontaneously organize into biology. The chemistry requires a physical mediator, a structured cradle that can bridge the gap between chaotic raw materials and a living system. In this volcanic landscape, the prebiotic gel first framework suggests early Earth was coated in sticky, porous, semi-solid matrices of hydrated clay and silica. This technical diagram outlines how gels solve the physical hurdles. Panels A and B show the gel's microscopic pores acting as a molecular trap, crowding molecules together to force interaction. The gel doesn't passively hold chemicals. Environmental forces like wave action create dynamic mechanical loading, physically pumping surrounding ions and molecules deep into the gel's matrix, as shown in Panel E. Once inside, Panel G shows the gel's mineral structure acting as a shield, blocking intense UVC radiation that would destroy delicate compounds. To solve hydrolysis, water inside a gel is bound to the matrix, reducing its activity. As Panel F shows, this tips the balance toward condensing new bonds rather than their destruction. By managing molecular concentration and shielding against radiation, the gel matrix provides a specific physical environment that permits complexity to emerge. To transition from dead chemistry to active metabolism, a system must operate far from thermodynamic equilibrium, continuously drawing in external energy to perform work. Panel H shows how the gel captures that energy. Embedded metal ions extract electrons from surrounding minerals, driving continuous redox reactions as a primitive chemical engine. This engine generates physical motion through chemomechanical coupling. As reactions cycle, changing chemical states cause the entire gel structure to autonomously pulse and shrink. This means the gel actively flushes out waste and draws in fresh nutrients on its own. It operates as an energy transducing entity, performing the physical work of a living system before the first cell ever existed. This diagram illustrates the final structural transition. In Panel C, we see a protofilm, where lipid molecules within the gel naturally reorganize into discrete compartments around successful chemical networks. These embedded protocells enter a bootstrapping phase, sharing resources and dividing metabolic labor with their neighbors within the protective matrix. Panel E shows the culmination of this communal phase, the emergence of LUCA, the last universal common ancestor. This fully realized cellular entity developed its biological machinery while safely anchored in the gel. Finally, following the arrows to panels F and G, LUCA breaks free. The cells leave the gel matrix to become planktonic explorers, drifting into the open ocean to colonize the planet. The cellular form represents a late-stage development in biogenesis, a specialized vehicle hatched from a gel incubator. Because cellular biology is the only life we have ever observed, our search for extraterrestrial life focuses almost exclusively on finding free living cells swimming in liquid water. But if early life requires a physical cradle to form, alien ecosystems might never have developed the need for motility, remaining in their original sessile state indefinitely. This opens up the possibility of xenofilms. On other planets, life might exist purely as complex gel-like matrices built from non-terrestrial chemistries, pulsating on the surfaces of rocks without ever forming a single discrete cell. To find life in the universe, we must expand our search parameters,